All right, so now we're going to look at linear momentum on unit 4, okay? And so the key part of linear momentum is the impulse momentum theorem, is that an integral of force over time is going to give you change in momentum, where we define the momentum as mass times velocity. Okay, now unlike work and energy, momentum is a vector quantity, so we got to think about the x and y components separately. That's a huge difference. It feels very similar sometimes when you're doing conservation of energy or conservation of momentum, but this is really just a derivation from Newton's second law of motion. But again, this is a vector quantity, so we got to think about which way is positive, which way is negative, and that makes momentum sometimes a little bit harder or more computationally intensive than, say, like work and energy. Okay, an impulse is required to change in momentum, and remember, because it's an integral, any area under the force time graph is going to give you that impulse, which is the change in momentum. So let's take a look at an example of doing that integral. So a multiple choice. Net force exerted on an object is given by f of t, where a is given by this. What is the change in momentum from 0 to 3 seconds? So we're just going to integrate from 0 to 3 of f dt. That's going to be the change in momentum there. That's all we're doing. So we'll make this at squared plus b. And because this is a numerical one, you can do this by hand, but just want to point out to you, you get to use Desmos given the digital exam format. And Desmos makes it really super easy to do something like this. You can just say integral from 0 to 3. You can even write at squared plus b dt if you want to add sliders for a and b. Then you just say like, oh, well, they told me a is 1 and b is 1, right? And so that's going to be 12. Okay, you can do that integral by hand, right? A lot of you guys are strong in math, so but there's no harm in just feeding it into Desmos to give you the answer. Okay, center of mass, sometimes thrown into like the second unit, but I think it's highly tied into the momentum section, so I still prefer to teach center of mass in the linear momentum. Like I said, College Board curriculum will sometimes put this into unit 2, but center of mass is really you're doing a weighted sum of the mass times its position divided by the total mass. In the integral form, you're integrated x times the mass of that this little chunk divided by the integral of this, which is the total mass. This is total mass. So this is the integral form of them. It's position times their mass divided by the mass. And then when you do velocity of center of mass, it's very similar equation here. All right, you're doing a weighted sum of the mass times their velocity over the total mass. But this quantity here is really the total momentum. It's the total momentum of every object in the system. M times v of every object in the system. So the whole idea is for center of mass is if you're made up of a whole bunch of different objects, you can use these to calculate the center of mass or the center of mass location or the velocity of the center of mass. And so just to keep that in mind, that is how we do that. And we might have to do that as an integral. And so let's go through an example where you might have to do that. So we have a triangular rod here, has a length L, mass m, and a non-uniform linear mass density given by this, where x is the distance from the end of the rod, x equals 0. Derive an expression for the center of mass of the rod. So the entire mass is m. They're giving you the density. So when we're doing the center of mass calculation, you're integrating x times dm. Now, how do we decide, and then divided by the total mass, which is m. Now, how do we do, what is dm, what is x? Is the whole idea is to say like, well, because you're trying to do the mass times its position, you want to chop it up into little chunks this way. Why this way? Because if it's really thin in this direction, like this thing has a width dx here, if it's really thin, then his location is just his x coordinate. Like it's not, like the problem with just center of mass in general is like the mass is different location distances from that left coordinate, right? And so if we make it super thin in the x direction, that is almost like a point mass, right? So the xdm and the mass of that thing, so what is the mass of that little segment there? It's the linear density times how long it is, because this is when they give you linear mass density, that is the mass divided by the length. So so mass over length is the linear mass density. Okay, so if I want the mass, I got to do the density times how long it is. Well, this thing's chopped up. Its thinness is dx. So the dm is going to be the lambda is 2m over L squared times x and then dx. And then x dm, which is what this integral is going to do, is x times this. That's going to make that x squared, right? So then we want to integrate this. That will handle that. Now, what do we want to, the x, well, we want to go from x equals 0 to L, right? 0 to L here. And so this one, x squared, the integral is x cubed over 3 from 0 to L. And that's going to be 2m over L squared. Plug in L, you're going to get L cubed divided by 3. Okay, and then if you plug in 0, you just get 0. So then 3 of those cancel. So you get 2 ml over 3. And then the center of mass is 2 ml over 3. That's the numerator, divided by m. So the m's cancel, and so you get 2/3 L. So for this guy, his center of mass is located around here, 2/3 of the way to L there. Okay? All right, conservation of momentum. So here's the huge part, right? If you consider the whole system and putting it together and you add this all up, if this guy here is 0, so if the impulse is 0, then the change in momentum is 0. And that is really useful. That's what we call conservation of momentum. That's very often we do it in a collision. If both objects are in the system, they collide, then we say the total momentum doesn't change if there's no external forces. They may exert forces on each other, but if you make the system all the objects involved in the collision, then overall there's no external forces on that system. All right, and so that's the huge part, is to identify this part. So kind of like work and energy, if you thought like work and energy, our problem solving process was to first identify the system, then consider what the work was, then consider the change in terms of work is change in energy. Here we're going to do impulse, right? Impulse is the change in momentum. So it's going to be the very similar process. We need to determine if there's an impulse. If there's an impulse, great. If it's 0, then the momentum is conserved. Okay, so that's going to be our problem solving process when we're going through these steps here. Let me pull those up real quick. So if we look at our problem solving steps, right? We want to identify the system, right? That's like just like in work and energy. When including both objects in a collision, the force internal system does not contribute to an external impulse. We want to draw a free body diagram, all right? Just like in work and energy. We would determine if an impulse is acting on the system. In a collision, if the time we assume is to be very short, so we assume the impulse of non-contact or non-normal forces is negligible. Impulse is a vector, so there may be impulse in the x direction, not the y direction. This is a difference in terms of how we handle it for work and energy. Work and energy, there's not vectors, so we don't consider x and y separately, but we definitely consider the x component of momentum and the y component of momentum and impulse in here. We're going to calculate the impulse, right, which is the f dt. We're going to calculate the initial momentum, final momentum, and then apply impulse is the change in momentum. So this is very, 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 very similar to work and energy, but we got to remember they are vector quantities here. Now, one thing to keep in mind is, why don't we do work and energy? How do you know to use linear momentum instead of work and energy? And the key thing is, in a collision, what happens is there may be a loss in energy in that collision due to the physical damage. That's not explicitly taught sometimes. It's like, why aren't we just using work and energy if it's so much simpler? Is because in a collision, you may lose some energy to other forms of energy that we don't model. Like when we did the work and energy unit, we only talked about certain kinds of energy, right? Spring potential, gravitational potential, kinetic. There are other forms of energy that can happen, especially internal energy in a system, that might not be modeled by our mechanical energy that we did in the previous unit. And so in those instances, when we might lose some energy to other forms of energy, we can't use work and change in energy, but momentum can save us, because for sure, the impulse, if there's no external impulse, there is absolutely no change in momentum. Now, note that in the center of mass system will, because the impulse is 0, and remember we talked about this, is the velocity of center mass is the momentum of the system divided by the mass of the total mass, that if the total momentum doesn't change, then the velocity and the mass of the total system doesn't change, and the velocity of the center of mass isn't going to change either. That's sometimes a little bit hard for people to understand, is that yes, in a collision, momentum might change for the individual objects, but it's because the total doesn't change, the center of mass of the system isn't going to change. Okay, elastic versus inelastic collisions, the only distinction is whether or not kinetic energy is conserved. Elastic collisions doesn't mean it bounces, it doesn't mean anything like that. It means kinetic energy was the same before the collision and after the collision. Inelastic collision means the kinetic energy was different from before the collision and after the collision. That's the only difference, and that's any justification around elastic or inelastic collisions are whether or not the kinetic energy is conserved. Okay? And then momentum is a vector quantity. So let's go through some conservation of momentum problems here. Okay. So blocks A or impulse momentum. Blocks A and B of masses 2m and m are arranged in a setup consisting of a ramp that makes an angle theta with a smooth horizontal table and an ideal spring constant k fixed to a wall as shown. Block A is held at rest at distance d. So at rest means velocity is 0 up here. and block B is at rest here on the table. The coefficient of kinetic friction between A and the rough ramp is mu. The region of length, this is where the frictional part is. There's negligible friction between the blocks in the smooth table. So this part is smooth, so there's no friction there. Block A is located at a horizontal position x0 and released from rest. After the block is released, the following occurs. At time t equals t1, block A has traveled the distance d, so t1 occurs and is moving with speed v at x1. So this is at t1 right here. So he's moving at a speed v at this point. Okay, and then at time t2, block A is at x equals x2. They collide at this point, so we have a collision. So we're thinking momentum during this collision part. Okay, but prior to that, there was no collision, so we might as well stick with work and energy for the prior part. But for the collision itself, before and after, we're going to do momentum because we might have lost energy. It sticks, so they move together. Time t equals t3, the combined blocks, they stick to the spring in equilibrium. So now we're going to hit the spring, and then they're going to at time t equals t4, it's not shown on here. It's going to be instantaneously at rest and the spring. So this is t4 right here where we compress it into there. So the collision, so there's motion here. We might probably use energy on. We'll use a collision. We'll use momentum. And then from here to here, it's colliding. But because this is massless, you don't really have to handle. There's no loss in momentum because this guy doesn't contribute any momentum because his mass is 0. Then from here to here, compressing a spring, probably work and energy. Okay, so there's kind of 3 phases that we're going to analyze this in, and that's how you decide which are the collisions, the momentum, anything else, probably just work and energy on this. Okay, so we want to derive an expression for speed v of block A at time t equals t1. So from here to here, there's no collision, so might as well stick with energy. So what's our system going to be? Our system is, because there's a change in height, it's going to be the block A plus the Earth. Okay, so we want to think if there's any work happening. Well, in this case, we're going to have gravity. We're going to have a normal force, and then we're going to have friction up the ramp, right? Nothing else is touching the block, so during that time we have that. Down here, we're just going to have gravity and normal force. Okay? Now, if we look at the displacement, because we're trying to decide if it does any work here. Here's the displacement. Here's the displacement. Okay, so normal force doesn't do any work because its direction of it is perpendicular to the displacement, so it doesn't do any work. Gravity doesn't do any work because it's internal to our system. Friction is going to do some work here. Okay, how about here? Well, both of these forces are perpendicular to the displacement, so neither of them do work. So the purpose of doing that free body diagram was just to establish what work was happening. And the work is going to be, it's negative work because friction is pointing up the ramp and displacement is down the ramp. So that's that. And if you think about inclined planes, because the acceleration is 0 in that direction, that should be negative mu mg cosine theta times d. That's our expression for the work. Now we want to think about the energies because we're only thinking about kinetic and gravitational potential because you have the Earth and the block. So we don't have any kinetic energy. We're going to say the bottom is where h equals 0. So we are going to have some height here. So we have some gravitational potential energy, but no kinetic energy. But what is that height? They didn't give it to us, but we know this is d. And so this is a triangle. You can say h, this height is d sine theta because sine of theta would be opposite of our hypotenuse. So this is mg d sine theta. Okay. Now the energy down here, all we have is kinetic energy because the gravitational potential is 0 because we're at a height 0 now. So we just have 1/2 mv squared. And we want to solve for that. And now we're going to do work is the change in energy. Right? This is the previous units review. So that's negative mu mg cosine theta d is equal to the final, which is 1/2 mv squared, minus the initial energy we found, which was mg d sine theta. So we're going to move this over to the other side. So we get mgd, and then we can make it sine theta minus mu cosine theta. You just factor it out. It's equal to 1/2 mv squared. M's cancel, can multiply by 2. Sine theta equals v, and then you just take the square root to get that v there, right? So something like that. So that's and that is in terms of those, yeah, we're using all of those variables. They're all valid variables for us to use. Okay, derive an expression for the spring constant. So now what's going to happen is they're going to collide. Okay, so we can't just say energy from here to here because during the collision, we might have lost some momentum, right? Oh, this was supposed to be 2m. Sorry, all these m's were supposed to be 2m for this one, but that's okay. They would have canceled anyway. Okay, so we have two masses that you're going to stick together. So we want to think about the momentum before, momentum after, and we also want to think if there's any impulse. Well, if you think about this system as a whole, there's going to be a force between the two blocks themselves. But as a system, right? So our system's going to be both blocks. All we have is gravity and normal force of the system itself, right? And so there's no horizontal impulse. So our system for this part is going to be the 2 blocks. The impulse is going to be 0 in the x direction, which means we can apply, that means there's no change in momentum in the x direction. So we want to think about the initial momentum before the collision. Well, the 2m is moving to the right with velocity v. It's 2mv. Plus this block is at rest. So this is 2m, and then we have the velocity here. Square root of 2gd sine theta minus mu cosine theta, like that. Okay, so that's the initial momentum. And then the final momentum is they're both going to be moving together, m plus 2m, with a final velocity. And so now we can figure out what that is. We just say that's equal to the initial, right? So that's going to be 3m. And you just divide this thing by 3m. So the m's will cancel, so you'll get the final velocity to be 2/3 square root of 2gd sine theta minus mu cosine theta. Now, why is that helpful? Is because we're going to say then, at this point, now we just have kinetic energy, and now we can do conversion into just the spring potential energy. So here we can say our system, from a work and energy point of view, is going to be the 2 blocks plus the spring. We're not going to include the Earth. Why are we not going to include the Earth? Because there's no change in height, right? So there's no gravitational potential energy to worry about. Or at least it's not changing, right? And so if you look at our forces here, you might have a spring force acting on it, right, when it collides. But that's internal to our system, and our displacement's to the right, so we're not going to have any work because these two forces are perpendicular. So anyway, so the end result is that the work is 0. So the initial energy is just kinetic energy, 1/2 3m times Vf squared. So we want to square this thing, so it's going to be 4/9. And then square just gets rid of the square root. Okay, and so, and then the final energy is going to be, so at the end, when it fully compresses, the velocity is 0. Remember, at max compression, it doesn't have any velocity left, so it's not going to be moving anymore. And so we're going to say, oh, it only has spring potential energy, right? And so we're going to say that, let's go ahead and cancel, let's see, 2 times 4 is 8. This is going to cancel to 3. So we're going to say it's 1/2, what is that, 8, let's leave that 1/2 there because it's going to cancel with this guy. Actually, let's not cancel the 3m. So you have 1/2, 3m, 4/9, 2gd, and then sine theta minus mu cosine theta. All right, so the 1/2s are going to cancel. Then you can cancel that to be 3. And so then you're going to have kxc squared is going to be m, let's see, this is 8/3 mgd sine theta minus mu cosine theta. It's just a lot of math operation at this point. You're going to divide by k and then take the square root, and that will be our xc. Okay, cool. All right, let's look at another problem. So we have a pendulum of length L consists of a block of 1 of mass 3m attached to the end of a string. Block 1 is released from rest, so the velocity is 0 here, with the string horizontal. At the bottom of its swing, block 1 collides with a block of mass m, which is initially at rest on the edge of the table of a height 2l. Block 1 never touches the table, okay, and as a result of the collision, block 2 is launched horizontally from the table, landing on the floor distance 4l from the base of the table. After the collision, block 1 continues forward and swings up. At its highest point, the string makes an angle theta max. With the vertical, air resistance and friction are negligible. Express all answers in terms of m, l, and physical constants as appropriate. Derive an expression for the angle theta max that the string makes with the vertical as shown in the original figure when the block 1 is at the highest point in the collision. Okay, so we got to think about the phases here. We're going to swing down, okay? So from there to there, from this point to this point, we're going to do energy to talk about how fast he's moving here. Then they're going to collide. They're not going to stick together. Doesn't mean that the kinetic energy is conserved. It didn't say an elastic collision, or it did not say it was elastic, but we are going to talk about the momentum there, and then we're going to figure out the velocity from there to there. And so we're going to put it all together on that front. So let's talk about the energy. Let's talk about order of the motion, right? So here, we're going to include the Earth in the block as our system. We're going to make this h equals 0 just for the purposes of figuring out how fast he's moving before the collision. So we'll call that V, I guess. So we'll say initially, how much energy does he have? And I'm just going to skip over the process of showing you that energy is conserved, because that's part of the unit 3 is do that system. You'll find that the work is 0 because the tension force doesn't do any work because it's perpendicular to the displacement. Okay, so the initial energy is mg, and what's the height is L. Like from here to here, that's L. Has no kinetic energy because released from rest. The final energy is 1/2 mv squared. So then we're just going to set them equal to each other. So you can solve for the velocity being square root of 2gl. Okay, so that's how fast he's moving there. Now they're going to have a momentum conservation, because you think about the system, there's no external horizontal forces, so the impulse in the x direction is going to equal the momentum in the impulse in the x direction is going to be 0. So the momentum in the x direction is going to equal is not going to change. So we have the mass m is moving at v, and the other mass of block 2 is moving at speed 0. So this is just mv, which is m square root of 2gl. The final momentum, okay, this is the tricky part. M is going to move with the speed v1, and then the other block is going to move with the speed v2, because they're going to have different speeds. And so that's going to equal m square root of 2gl. You can divide the m's. So you get v1 plus v2 equals square root of 2gl. Now, a couple of things. I need to know v1 so then I can figure out how much it's going to swing up, right? That's the main idea there. So in order to do that, I need to know v2, right? Like, because I have 2 unknowns, so I got to figure out. But they gave us information. This is a projectile motion question, is to figure out, oh, how fast was he moving up here in order to launch this way? So I can solve for v2 by thinking about projectile motion. So that's what we're going to do. We're going to look at the x and the y. And this is just projectile motion, so we're not going to use calculus for the kinematics. But this is back to our unit 1 stuff, right? From here to here. We'll say right is positive, and because he's going down, we'll make down positive. Okay, so if we think about his displacement from there to there, he goes to the right 4L, and he falls the distance 2L, and that's positive 2L because I said down was positive. The initial velocity is the v2, and in the vertical direction, it's 0 because the velocity is only horizontal. You can see that on the path up here. It has a horizontal, launched horizontally. Final velocity, don't really know, but we know the acceleration is 0 in the x direction, and it is positive g in the y direction because I said down was positive. Okay, and so this one, I don't have enough information. I need to know either the time. Oh, I need to know the time or the final velocity so I can solve for that. But here I can solve for the time on this side because remember the time is shared. So what kinematic equation can I use here is going to be this equation. So we get 2L is 1/2 gt squared. So t is going to be square root of 4L over g, which is 2 root L over g if you want to simplify it that way. So this is 2 root L over g. And so then what we're going to get is we're going to use the same equation over here. So we're going to get 4L is just v2 times 2 root L over g. That will cancel to 2. And so your v2 is going to be 2L over root L over g, which is 2L times square root of g over L. And you could bring that L inside, actually. It'd be 2 square root of L squared g over L. Because when it goes inside the square root, you got to square it, which is going to be 2 root LG. You can plug that into here. So this is square root of 2 LG. So then the V2, all right, so the V1 is going to equal 2 root LG. Or sorry, plus this is going to equal root 2 root LG. So you're going to move it over. Actually, it's going to bounce backwards. Interesting. So if you factor out the root LG, it's going to be root 2 minus 2. Okay? So it actually is going to bounce backwards. So I probably just don't have the picture right. It's going to bounce back this way. It's not super important, but it's going to bounce the other direction. Okay? And so then what do we want to say at this point is that we say like, okay, we bounce back that direction. So what is that theta max? We then have to think about the energy. So it's the reverse of this process. We're going to say, oh, the initial energy is 1/2 m times v1 squared. And then the final energy is going to be mgh, right? So you can have 1/2 m v1 squared. Just square this is going to be lg times square root of 2 minus 2 squared. Or actually, we got to square this guy. Is equal to mgh. We can solve for the height. Okay, so the g's will cancel. So the height is going to be 1/2 L square root of 2 minus 2 squared. Okay, now how does that factor in? Let's kind of make this picture a little bit easier. How does that factor into figuring out what the height is? Oh, so we know the height here. How do we figure out the theta? Well, we know this distance here is L. We know this distance here is L because it's a string. And if we think about this part, okay, this part here, think about a right triangle, this part here is going to be L cosine theta. So the height is L minus L cosine, because if this whole thing is L and this part is L cosine theta, then this has to be L minus L cosine theta. Okay, so then that's what the h is equal to. So the h is going to be L minus L cosine theta is equal to 1/2 L square root of 2 minus 2 squared. You can factor out the L here and cancel it. Make those 1. And then the L's cancel. And so then you get cosine theta is going to be, cosine theta is going to equal 1 minus this guy here, 1/2 square root of 2 minus 2 squared. And let's see what that number is. I hope it comes out to be a nice number because I modified some things on this question. So I hope it 2 squared times 0.5, then plus 1. You get this is equal to 0.828. And so then you do cosine inverse, and you get the theta is equal to 34 degrees. Okay, that is theta max. Okay, part B is a different area. Suppose the blocks then had an elastic collision, and block 2 traveled the distance d. Block 1 still went up the same theta max as before. Would the distance to where the block landed, d, be greater than, less than, or equal to 4g? Well, if an elastic collision, we no loss in energy. So if he goes the same angle, bounces back at the same angle, then this guy's going to have more energy. So he's going to travel further. So it's going to be a larger d. Larger d. Because the total kinetic energy increases. Because none is lost in the collision. And that implies more speed for block 2. Okay, and so now we want to derive an expression for d. How are we going to do that if it were an elastic collision? Actually, I don't want to do this question. This one probably is a little bit too advanced, and the math might get a little too hairy into there. So just wanted you to understand that how those things are related conceptually, okay? So now we're going to look at the last part of the momentum is the real second law of motion, okay? It's not F equals ma. That's what we did. It's actually F is the derivative of the momentum, and you can look at this from the integral form. F dt is the change in momentum. This is the integral form. It's actually the derivative of the momentum. So what it is, it's the derivative of m times v, technically. Now, most of the time, the mass is constant. And if it's constant, then you can pull that out, and then it becomes m times dv dt, which we call ma, which is what we're so used to, and what we did in Unit 2. But if m is not constant, which is something that you will see now in the new version of mechanics, then you see this question, then you actually have to do product rule. In general, it's equal to product rule, it's m dv dt plus v dm dt. Okay, this is a more general form if the mass is changing. Okay, so let's go through an FRQ. One example of this, I want you to just, because this is again like a more general form of Newton's second law. So if a cart initial mass has an initial mass of m0, is moving along a track with v0. The cart contains sand, and a small hole at the bottom allows sand to leak out at a constant rate. So sand is leaking out at a rate r. And that is really, like how much mass in kilograms per second. That's how much mass is leaving. And sand fall vertically downward without affecting the motion of the cart horizontally. There's no external horizontal force in the system. Okay, what that means is there's no forces acting on the sand and the cart. They're just kind of going along. Derive an expression for the velocity of the cart. Okay, so this is one of those things where we know there's no force, but there is clearly a change in momentum that's going to happen on here if the mass is kind of going straight down. We want to think about it as the change in momentum being 0, right? So this is, the derivative of this is going to be m dv dt plus v dm dt has to equal 0. Now, normally this is 0, then we say, okay, dv dt is 0. However, in this case, the mass is being reduced by r. So dm dt is negative r. So we have m dv dt minus rv equals 0. And look at this. M and r are constant, and we just have an equation with v. We can do this as a differential equation. And we separate a separation of variables, so we get dv over v. Move the dt and the m to the other side, r over m dt. We can integrate. You can do bounds of integration if you want, or you can just say absolute value of v is going to be r over mt plus c. Put e as the base, and then strip away the absolute value, becomes c e to the r over mt, right? And then, well, times 0, we know the velocity is initially v0. So then we know v0 equals c e to the 0, which is c. So c is equal to v0, so our velocity equation is going to be v0 e to the r over mt. Okay, so that's part A. Explain whether the cart's acceleration is constant, decreasing, increasing, decreasing, or 0 as time progresses. Okay, so we can do that from our equation, but it's going to be increasing. This is exponential. It's going to exponentially grow. It's going to be increasing. And there's a couple of ways you can think about it, but you honestly can look at this part here, dv dt is equal to r over mv. This is the acceleration. Or look at this guy, the acceleration is just the derivative of the velocity. You can do either way, derivative of this thing, which is going to equal r over m v0 e to the r over mt. And the exponential part just gets bigger and bigger over time. All right, and so we get to that point, and that is our answer. So I wanted to just make sure you were exposed to that. Some of the practice tests I saw have done some things like this, so I want to make sure you know how to handle cases where the mass is inconstant.